ಇದು ನೆಕ್ಸ್ಟ್ ಎತ್ಲಿ ಬಿಟ್ಟಿಲ್ಲ ನೆಕ್ಸ್ಟ್ ಎತ್ಲಿ ಬರೋದು ನೆಕ್ಸ್ಟ್. Okay, today our topic is electrical design of overhead lines. Myself is Dr. G. Venkat Subbareddy, Associate Professor of Triple Department, G. Polarity Engineering College. Electrical design of overhead lines. The transmission of electric power is done by three-phase and three-wire lines, overhead lines. In AC transmission system, the resistance, inductance, and capacitance are uniformly distributed along its length. These are known as a constants or parameters of the line. These constants would determine whether the efficiency and voltage regulation of the line will be good or poor. Therefore, a sound concept of this constant is necessary in order to make electrical design of a transmission line a technical purpose. The transmission line has inductance, resistance, and capacitance. The three elements are uniformly distributed for entire length of the transmission line. In this element, first element is nothing but resistance. The property of resistance is to oppose the flow of current to oppose the flow of current. Inductance is nothing but while alternating current flowing through the conductor, a changing flux is set up with and which is linked with the conductor. Due to these flux linkages, conductor possesses inductance, and the mathematically defined as flux linkages divided by current is known as inductance. Capacitance. Third element is capacitance. We know that two conductors are separated by an insulating material constitute a capacitor. As any two conductors of overhead transmission line are separated by air which acts as insulation. Therefore, capacitance consists between any two of overhead line conductors. Capacitance is defined as Q divided by V. The charge on conductor divided by the potential difference between the two conductors is known as capacitance. The resistance of transmission line. The resistance of transmission line conductors is the most cause of power losses. I square R is nothing but a power losses in the power losses. The definition of R is equal to rho L by A. Rho is nothing but a specific resistivity and L is nothing but length of the conductor. A is nothing but cross sectional area of this conductor. Then temperature variation, the resistance is also changes. R2 is equal to R1 into 1 plus alpha 1 into T2 minus T1. Then alpha 1 is nothing but a temperature coefficient at T1 degrees centigrade. Alpha 1 is defined as alpha naught divided by 1 plus alpha naught into T1. Alpha naught is nothing but a temperature coefficient at 0 degrees centigrade. In case of single phase two wire line, the total resistance is nothing but that is called a loop resistance equal to double of the resistance of each conductor. But in case of three phase line, the resistance per phase is the resistance of one conductor. One more important point in case of AC, that is nothing but a skin effect. The tendency of alternating current to concentrate near the surface of the conductor is known as a skin effect. Due to skin effect, the cross-sectional area of the current flowing through the conductor is reduced. Consequently, R is equal to rho L by V. When cross-sectional area is reduced, then resistance is increases in case of AC circuit during the skin effect. That is nothing but skin effect. There is no current flowing through the middle of the conductor. Current flows only the surface of the conductor. Skin effect depends upon normally the nature of the material, and skin effect increases when increasing the diameter. Skin effect is also increases with increase in frequency. Skin effects is also depends upon the shape and size of the wire. Less less for standard conductor as compared to the solid conductor. Here, when the frequency is less than 50 Hz and the diameter of the conductor is less than 1 centimeter, skin effect may be negligible. While evaluating the inductance, before evaluating the inductance definition is nothing but flux linkages divided by current. For that reason, we calculate the flux linkages due to the single current carrying conductor through the internal flux as well as external flux. After getting the flux linkages divided by current, that can be defined as a inductance. For that reason, we calculate the flux linkages of a single carrying conductor. Consider a long straight cylindrical conductor of radius R meter carrying the current is I amperes, that is nothing but RMS as shown in the figure. When current flowing to the conductor, flux lines will be produced inside as well as outside the conductor. These flux linkages contribute the inductance of a conductor. Then flux linkages due to the internal flux. Flux linkage due to internal flux. First we define as magnetic field intensity. Magnetic field intensity at a distance of x from the center of the conductor is Ix. Hx is equal to Ix divided by 2 pi x. For internal flux linkages, the Ix is not a uniform current density. To make the Ix is uniform current density in terms of Ix is equal to pi x square divided by pi r square into Ix, then x square divided by r square into I. Hx is equal to x divided by 2 pi r square into I. But magnetic plus density is equal to magnetic field intensity into permeability. That is nothing but B naught is equal to mu r into Hx, mu 0 mu r into Hx, mu r is equal to 1 for non-magnetic material, then Bx is equal to mu 0 into Hx. Substitute here Ix value, then we get, then after getting the Bx, then point the total flux through a cylindrical cell of radial thickness dx and axial length 1 is meter given by the flux is equal to flux density into cross sectional area, flux density into 1 meter length, and the dx is a radial thickness. Then substitute here d pi is equal to bx into 1 into dx. That value is equal to mu 0 x into I divided by 2 pi r square Weber. But this d pi is related to only Ix, that is nothing but flux linkages with the conductor. Then the flux linkages d pi is equal to pi x square divided by pi r square into d pi. This is only for internal flux, not external flux. External flux is nothing but the current is uniform current density. For that reason, we directly consider as a I. But in case of during the internal flux, we instead of I, we consider as a Ix. The value of Ix in terms of I, x square divided by r square into I. Then plus total flux linkages in the conductor, integral of 0 to r mu 0 I into x cube divided by 2 pi r square into dx. When differentiating and substitute the limits, finally you get mu 0 I divided by 8 pi Weber turns per meter length. That is nothing but a flux linkages due to the internal flux. Next, for finding the total flux linkages, we calculate flux linkages due to the external flux. External flux is extended from the surface conductor to the infinity. Field intensity at a distance of x meters from the outside is given by same similar expression. Hx is equal to in case of internal flux, I is considered as Ix, but in case of external, the current is assumed to be uniform current density. For that reason, Xx is equal to I divided by 2 pi x ampere turns meter. Flux density same formula is applicable here. Bx is equal to mu 0 into Hx, mu 0 I divided by 2 pi x into Weber per meter square. Now the flux d pi through a cylindrical cell of thickness dx and the axial length is 1 meter, then d pi is equal to bx into dx. Mu 0 I divided by 2 pi x into dx is Weber. The total flux links the conductor at once only once. Then flux linkages d pi is equal to d psi, that is equal to mu 0 I divided by 2 pi x. Then the total flux linkages of the conductor from the surface to infinity, phi external is equal to integral of r to infinity mu 0 I divided by 2 pi x into dx Weber turns. Then overall flux linkages, that is nothing but the total flux linkages, flux linkages due to the internal flux plus flux linkages due to the external flux. Flux linkages due to the internal flux is equal to mu 0 I divided by 8 pi. Flux linkages due to the external flux is equal to integral of r to infinity mu 0 I divided by 2 pi x into dx. Finally, you get the flux linkages formula mu 0 I divided by 2 pi into 1 by 4 plus integral of r to infinity dx by x. This formula is very useful for calculation of inductance, single phase two wire line and three phase symmetrical spacing and three phase unsymmetrical transposed configuration, finally in case of double circuit line. For evaluation of inductance, this flux linkages is very important. First, inductance of single phase two wire line. Let us consider a two conductors A and B. At a distance of these two conductors will be D, and the radius of each conductor will be R. The current in the conductor A is Ia, the current in the conductor B is Ib. Because of one is a going conductor, the another one is a return conductor, the magnitudes of two conductors will be same. Then Ia is equal to minus Ib, then Ia plus Ib is equal to 0. The flux linkage is conductor A due to its own current mu 0 Ia divided by 2 pi into 1 by 4 plus integral r to infinity dx by x. Flux linkages with conductor A due to Ib. Because of There will be flux linkages with conductor A due to its own current of Ia and also mutual inductance of current Ib on the conductor. Then add these two equations, then we get the total flux linkages with conductor A, then we get mu 0 Ia divided by 2 pi into 1 by 4 plus integral of r to infinity dx by x. That is nothing but flux linkages with conductor A due to its own current plus flux linkages due to the conductor A due to the current Ib, that is equal to mu 0 Ib divided by 2 pi integral of d to infinity dx by x. Then simplify this expression by using mathematical analysis. Finally, we get the inductance of the conductor 2 into 10 power minus 7 ln d by r dash. D by r dash. Loop inductance is nothing but in case of single phase two wire line, the total inductance is equal to double of the inductance of each conductor. For that reason, loop inductance is equal to 2 into La Henry per meter. Then loop inductance is equal to 2 into 10 power minus 7 2 into 2 into 10 power minus 7 into ln d by r dash. Then r dash is nothing but a self gm of the conductor, that is equal to 0.7788 r. This is nothing but inductance formula for single phase two wire line. Similarly similarly in case of in case of three phase overhead line, d1 d2 d3 are the distances between the conductors. D1 is the distance between B and C, d2 is the distance between A and C, d3 is distance between A and B. Then here, to find the inductance of conductor A, to find the flux linkages due to the conductor A due to its own current and mutual inductance effects of IB and IC. Mutual inductance effects of IB and IC. Then flux linkages of conductor A due to its own current mu 0 Ia divided by 2 pi into 1 by 4 per integral of r to infinity dx by x. Assume that the currents are balanced. Ia plus Ib plus Ic is equal to 0. Ia plus Ib plus Ic is equal to 0. Flux linkages with conductor B, the mutual effect I mu 0 Ib divided by 2 pi into integral of d3 to infinity dx by x. D3 the distance of B from A, and flux linkages with conductor A due to IC mu 0 Ic divided by 2 pi integral of d2 to infinity dx by x. The total flux linkages with conductor A, that is equal to expression 1 plus 2 plus 3 mu 0 Ia divided by 2 pi integral of 1 by 4 integral of r to infinity dx by x plus mu 0 Ib divided by 2 pi integral of d3 to infinity dx by x plus mu 0 Ic divided by 2 pi integral of d2 to x into dx by x. Here Ia plus Ib plus Ic is equal to 0. By taking the balanced condition, the substitute here, then flux linkages with the conductor A mu 0 divided by 2 pi into 1 by 4 minus log r base c into Ia minus Ib into log base e d3 minus Ic into log base 2 de. Then substitute here symmetrical spacing. Then this formula is applicable for symmetrical or unsymmetrical transpose configuration. In case of symmetrical spacing, if three conductors or ABC are placed symmetrically at the corners of equilateral triangle, then that spacing is said to be symmetrical the side of D. Then D1 is equal to D2 is equal to D3, that is equal to D. Under some circum conditions, the flux linkages with conductor A, substitute here in the above expression, D3 is equal to D and D2 is equal to D, and simplify this expression. Finally, we get inductance of conductor A, La is equal to 2 into 10 power minus 7 ln d by r dash. That is nothing but inductance of a three-phase overhead line when the conductors are placed symmetrically. In case of unsymmetrical spacing and transposed configuration, to avoid unequal voltage drop and inductive interference with the neighboring communication system, we go for unsymmetrical spacing. When three-phase line conductors are equidistant from each other, the conductor spacing is said to be unsymmetrical. In order that voltage drops are equal in all conductor, we generally interchange the positions of the conductor at a regular interval along the line so that each conductor occupy the original position at every other conductor of an equidistance. Such exchange of position is known as a transposition. Under such conditions, the flux linkages and inductance of each phase is not same. A different inductance in each phase as a result, unequal voltage drop in three phases even if the currents in the conductors are balanced. Therefore, voltage at receiving end will not be same for all three phases. Then the above figure, this figure is shows unsymmetrical transposed configuration. The unsymmetrical and transposed configuration. In this expression, IA is taken as a reference, then IB and IC value is taken in terms of IA. For that reason, we define an operator of A. A can be defined 1 at an angle of 120 degrees. Every vector is multiplied by A. The vector magnitude will be same and this vector is rotated anti-clockwise direction by 90 degrees. For that reason, IA is taken as a reference IB is equal to A square into IC is equal to A into I. The properties of A, 1 plus A square is equal to 0 and A cubed is equal to 1. These are the properties of A. IA is equal to I at an angle of 0, IB is equal to A square into IC is equal to A into I, then A square is equal to in rectangular form minus zero point 0.5 minus j 0.866, I value in rectangular form minus zero point 0.5 plus j 0.866. A is equal to 1 at an angle of 120 degrees, A square is equal to 1 at an angle of 240 degrees, A cube is equal to 1 at an angle of 360 degrees. Finally, the properties of A is equal to 1 plus A square is equal to 0 and A cubed is equal to 1, A power n is equal to A power n minus 3, A power 4 is equal to 1, A power 5 is equal to A square and A power 6 is equal to A power n minus 3, 6 minus 3 is equal to 3, that is equal to 1. That is nothing but the properties of A. These can be used for one phase is taken as reference, remaining two phases can be measured for the first phase. By taking all these values, IA is equal to IB is equal to I into minus zero point 0.5 plus minus j 0.866 I, and IC is equal to minus zero point 0.5 plus j 0.6866 into I, then substitute in the formula, then finally for derivation, derive the expression, finally we get LA is equal to 2 into 10 power minus 7 ln cube root of d1 d2 d3 divided by r dash. This is formula for inductance. Formula for inductance of three phase unsymmetrical spacing. Then inductance for phase in case of double circuit line 2 into 10 power minus 7 ln dm by ds is nothing but 0.7788 into r. dm is equal to d1 d2 d3 whole power 1 by 3. Self GMD or self GMR concept is used only for evaluation of inductance only. Self GMD, then this can be proved that R dash is equal to 0.7788 into R, that is nothing but self GMR of the conductor. Self GMD depends upon the size and shape of the conductor and independent spacing between the conductor. In case of mutual GMD is nothing but is simply geometric mean distances between the conductors. That is nothing. In case of single phase two wire line, the mutual GMD Dg is equal to small d. In case of three phase unsymmetrical spacing, Dm is equal to d1, d2, d3 whole power 1 by 3. While considering the double circuit line, ABC and A dash, B dash, C dash, R is nothing but a radius of the conductor. Then self GMR conductor is 0.7788 R. By using these conditions, the self GMD of phase A dash ds1, the self GMD of phases B and B dash ds2, and the self GMD of phases C and C dash ds3. Equivalent self GMD of one phase ds is equal to ds1, ds2, and ds3 whole power 1 by 3. Then ds is same for all three phases. Similarly, we calculate the mutual GMD for double circuit line. DAB is equal to DAB into DAB dash and A dash B dash whole power 1 by 4. Mutual GMD between the phases B and C. DBC is equal to DBC into DBC dash DB dash C into DB dash C dash whole power 1 by 4. Mutual GMD between the phases C and A is equal to DCA, DCA dash, DCA dash C and DA dash C dash whole power 1 by 4. Equivalent mutual GMD DM is equal to DAB into DBC into DCA whole power 1 by 3. Then after calculating of DS and DM, then finally the inductance of double circuit line 2 into 10 power minus 7 ln d by dm divided by ds. Mutual GMD depends upon only spacing between the conductors and independent of exact size, shape and orientation of the conductor. These are the important formula for evaluation of inductance. For single phase line, 2 into 10 power minus 7 Lm d by ds. Here ds is equal to self GMR of the conductor 0.7788 into R. Dm is equal to spacing between the conductor, that is small d. In case of single phase 3 wire line, 2 into 10 power minus 7 log base c dm by ds. Here dm is equal to d1, d2, d3 whole power 1 by 3. That is the geometrical spacing. In case of double circuit line, ds is equal to ds1 into ds2 into ds3 whole power 1 by 1, and dm is equal to dab into dbc into dca whole power 1 by 3. Then inductance per phase per meter is equal to 2 into 10 power minus 7 log base c dm divided by ds. Some important formulas for evaluation of inductance. These are the concept of inductance. In case of inductance, we derive the expressions for single phase two wire line, three phase symmetrical spacing, three phase unsymmetrical transposed configuration, and finally we evaluate the values of double circuit line. These are the formula, these are the simple problems on inductance. Some problems on double circuit line also. This is nothing but hexagonal arrangement. Next, capacitance is defined, and next we derive the expressions for capacitance. This is electrical potential. The electrical potential at a point due to the charge is the work done to bring a unit positive charge from infinity to that point. Potential of the charge single conductor. Let us consider a single conductor at a distance of p from the hex. Charge on this conductor is qa. Charge on conductor is qa. Then E is equal to qa divided by 2 pi x into epsilon naught voltage volts per meter. Qa is equal to charge per unit length. E is equal to permittivity of free space. The approach as x approaches to infinity, the E approaches 0 because x is in the denominator, which is inversely proportional to voltage. The potential of the conductor in group of charged conductor, the potential of the conductor due to the current Ia and mutual current effect between other three conductors. The potential Fa due to its own charge, potential of conductor A due to the charge of Qb, like that, the potential of the conductor due to the charge Qc. Add all this value, then we get total potential difference from conductor A to the infinity neutral plane. Then finally, assume that balanced conditions, Qa plus Qb plus Qc is equal to 0, then substitute here, then we get V3 is equal to 2 pi epsilon naught QA log R base C log base C into 1 by 4 plus QB into log base C 1 by D1 and QC is equal to log base C 1 by 2 up to dash dash. The same expressions can be derived in case of capacitance also. Capacitance of single two wire line. Let us consider a two conductors at a distance of d meters. The charge on one conductor is plus q. The charge on other conductor will be minus q. Then applying the potential difference between the conductor and infinite neutral plane, Va is equal to integral of R to infinity Q divided by 2 pi epsilon x into epsilon naught plus integral of d to infinity minus qb into 2 pi epsilon into dx. Q divided by 2 pi epsilon naught log infinity by R base c minus log infinity by d2 base c. Then we get Q divided by 2 epsilon naught log base c d by r. Similarly, potential difference between the conductor B and infinite neutral plane Vb is equal to integral of R to infinity minus q divided by 2 pi epsilon x into epsilon naught into dx plus integral of d to infinity q divided by 2 pi x into epsilon naught into dx. Then we get Vb value. Then potential difference between the two conductors Vab is equal to Va minus Vb. Then substitute here q divided by 2 pi epsilon naught into log base c d by. Finally, capacitance is equal to q by V. The charge per unit potential difference that can be defined as a capacitor. CAB is equal to Q divided by VAB. Q divided by VAB. C is equal to pi epsilon naught ln d by r dash. Capacitance to neutral. Capacitance neutral is equal to double of the capacitance of each conductor. The capacitance to ground or capacitance neutral is equal to 2 wire line, the twice the line to line capacitance. Capacitance of three-phase overhead line. In three-phase transmission line, capacitance of each conductor is considered as instead of capacitance from one conductor to another conductor. Symmetrical spacing. The spacing between the each conductor will be same. That spacing is said to be symmetrical spacing. Then three conductors ABC are three-phase overhead transmission line having the charges QA, QB and QC and meter per meter length of respectively. Let the conductors be equidistant or d meter from each other. We shall find the capacitance from the line conductor to neutral in symmetrical space line. The overall potential difference between conductor A to infinite neutral plane that is equal to VA. VA value is equal to 1 by 2 pi epsilon naught QA into log base C into 1 by R plus QB plus QC into log base C 1 by D. Assuming that balanced supply QA plus QB plus QC is equal to 0, QB plus QC is equal to minus QA, substituting here, then we get the capacitance C is equal to Q divided by V, then we get 2 pi epsilon naught into log base C d by R. In case of unsymmetrical spacing, the unsymmetrical transpose configuration, every conductor is occupy the original position at equidistance. Such exchange of position is known as a transposition. QA balanced condition QA plus QB plus QC is equal to 0. Then calculate all three sections of transposed line. The potential in first position V1 is equal to 2 pi epsilon naught QA is equal into log V 1 by R plus QB into log by C 1 by D2 plus QC into log by C 1 by D3. Then simplify this one. Average potential difference with conductor A, VA is equal to one third of VA plus VB plus VC. Then substitute here. Then we get CA is equal to 2 pi epsilon naught into log BC cube root of D1 D2 D3 divided by R. That is nothing but a capacitance of three phase unsymmetrical. These are some important formula problems on capacitance. These are some important formulas on capacitance. Thank you.